Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 10, and today we're looking at Section 10.5 on absolute convergence and the ratio and root tests. All right, so up until now, if you look at the last several tests for convergence that we've looked at, they have all required that the series has positive terms only. At least eventually, right, from some term on. So now we're going to lose that requirement and talk about series that have negative terms throughout. And so the first thing we're going to talk about is absolute convergence. A series A sub n converges absolutely or is absolutely convergent if the corresponding series of absolute values, sum of absolute value A sub n, converges. And the reason that that's a helpful term to have is because it turns out that a series that converges absolutely also converges. And that is called Theorem 12. So you'll notice that in the original PowerPoint, it said Theorem 16, and I typed a little 12 over top. And that's because the last time I taught this course, I noticed that they had updated the edition of the textbook, but they had not made the updates in the PowerPoint. So in some previous edition of the book, this was called Theorem 16. In the current edition, it's called Theorem 12. All right, and that is called the absolute convergence test. And so again, what it basically says is that if a series converges absolutely, then it also converges. So what's good about that is that if you have a series with a bunch of negative terms, for example, an alternating series, the first thing you can do is look at, okay, what does the series look like if you just make all of the terms positive? And if that series converges, then your original series also converges and you don't have to think about it anymore. Okay. All right, so now we're going to talk about a couple of tests that can be used on series with negative terms. And we're going to start with the ratio test. So the ratio test is a generalization of geometric series. Recall that a geometric series has a constant ratio R between consecutive terms, and the series converges if the absolute value of R is less than 1. It turns out this can be generalized to series where the ratio is not constant. And that's called Theorem 13. And I retyped it myself because there were too many changes in what was printed on the PowerPoint and it was bothering me. So I had a few minutes, I just retyped it. So Theorem 13 is called the ratio test. Let A sub n be a series, and suppose that the limit as n increases without bound of the absolute value of A sub n plus 1 over A sub n. So this is the ratio between the n plus first term and the nth term. We're going to call that limit rho. This is the lowercase Greek letter rho, R-H-O, the Greek version of the letter R. All right, it turns out that the series converges absolutely and therefore converges if rho is less than 1, just like with your geometric series. This time we don't have to talk about the absolute value of rho because we already took the absolute value here. So rho will never be a negative number. The series diverges if rho is greater than 1 or is infinite. All right, now what about the case where rho equals 1? Well, with a geometric series, if r equals 1, the series diverges. Unfortunately, that does not transfer over to the ratio test. If you use the ratio test and rho equals 1, the test is inconclusive and you have to try a different test. All right, so for the first two examples, we're going to look at these two series and use the ratio test to determine if the series converges absolutely or diverges. So let's go over to the tablet. And away we go. All right. So to use the ratio test, you have to look at the limit as n increases without bound of the absolute value a sub n plus 1 over a sub n. So in this case, a sub n plus 1 is equal to negative 1 to the n plus 1 times n plus 1 plus 2. You know what? I think I'll just show all my work here. Sometimes, depending on this general term, it's tricky replacing n with n plus 1, believe it or not. You have to be careful. Okay, 3 to the n plus 1. And then we're going to divide that by negative 1 to the n times n plus 2 over 3 to the power n. Okay. All right, so when you divide negative 1 to the n plus 1 by negative 1 to the n, you have one more factor, negative 1 upstairs than you do downstairs, so that's just going to leave a negative 1. And that negative 1 is inside absolute value, so we can actually ignore that. Okay. So now what I'm going to do is, instead of dividing by n plus 2 over 3 to the n, I'm going to multiply by the reciprocal. You're going to find yourself doing that a lot when you use the ratio test, because it's very common for the general term of a series to be a fraction. So here is a sub n plus 1. Instead of writing n plus 1 plus 2, now I'll just write n plus 3 over 3 to the n plus 1. And now I'm going to multiply by the reciprocal of a to the n, which is 3 to the n over n plus 2. Okay, so we have 3 to the n over 3 to the n plus 1. We have one more factor of 3 downstairs than we do upstairs, so we can get rid of those and just leave a 3. And now we can forget about the absolute value, because everything inside the absolute value is positive. Really, all the absolute value did was kill that negative 1. So we are left with n plus 3 over 3 times n plus 2. All right, and so by that Calc 1 shortcut about rational functions, limits at infinity, we just look at the ratio of the leading coefficients, because the top and the bottom are both degree 1. The leading coefficient upstairs is 1, leading coefficient downstairs is 3. Rho is 1/3, which is less than 1. And therefore, this series converges absolutely. And therefore it converges. All right, I like the ratio test. Okay, next example, the sum n going from 1 to infinity of n times 5 to the n over 2n plus 3 times natural log n plus 1. All right, so once again, we have to look at the limit as n increases without bound. And this time I'll just cut right to the part where I say n, a sub n plus 1, which is n plus 1 times 5 to the n plus 1 over. So here's an example of where you have to be careful. I'm replacing all the n's with n plus 1s. For that 2n plus 3, you got to make sure that the whole entire n plus 1 gets multiplied by 2. Okay, so that's going to go here like this. And then natural log n plus 1 plus 1. Nothing tricky about that one. Let's just write that as n plus 2. Okay, and now instead of dividing by a sub n, I will multiply by the reciprocal, which is 2n plus 3 natural log n plus 1 over n times 5 to the n. All right, so far so good. Unfortunately, there's not a whole lot here we can cancel. We can cancel 5 to the n into 5 to the n plus 1 is going to leave a 5. Other than that, we are pretty much stuck with everything else. So now, why don't we pull this 5 outside? And we can also lose the absolute value because everything in there is positive. Okay, so that's going to leave us with n plus 1 times 2n plus 3 times natural log n plus 1 over, okay, what's the first factor downstairs? It's twice n plus 1, add 3, which is 2n plus 2 plus 3. That's 2n plus 5. And we also have an n, and we have a natural log n plus 2. Right? Okay. So, let's see. This part of it is a rational function. Those are both polynomials of degree 2, and they both have leading coefficient 2. So the limit of that part is just going to be 2 over 2. So I'm going to write this as 5 times 2 over 2 times limit n approaching infinity, natural log n plus 1 over natural log n plus 2. Okay, almost there. So you might have an idea, hopefully you do have an idea of what the limit, of what that limit is, okay? Okay, I don't see any shortcuts, so I think I will just go ahead and use L'Hopital's rule. Okay, so right here using L'Hopital. So now I'm doing something that feels weird to me. I am differentiating with respect to n. And I think sometime a while back, I mentioned that that was something I didn't really like to do because n is not a continuous variable. But I am going to just suck it up and do it. I don't feel like writing an extra step to change the variable to x. So the derivative of natural log n plus 1 is 1 over n plus 1. The derivative of natural log n plus 2 is 1 over n plus 2. Now there is a chain rule issue there that I'm kind of glossing over. The derivative of n plus 1 and the derivative of n plus 2 are both 1. Okay. All right. So now if you just rewrite this as, I feel like I'm really belaboring the point here. All right. Okay. Instead of dividing by 1 over n plus 2, I'll multiply by n plus 2 over 1. This is n plus 2 over n plus 1. That limit is 1 for the same reason as the other few limits of rational functions. And therefore, the whole entire big limit is equal to 5. All right, what was the question again? Oh, the question was, does it converge absolutely or does it diverge? Well, that circled number is the value of rho. And what theorem 12 says is that whenever rho is greater than 1, the series diverges. And so I think I can squeeze that right in here. Rho is greater than 1. So series diverges. All right. And that's the ratio test. So back to the presentation. All right, next we have the root test. The root test will also tell you if a series converges absolutely or if it diverges. And it can also be used on series with negative terms. Let A sub n be a series, and suppose that the limit as n approaches infinity of the nth root of the absolute value of A sub n is equal to rho. Well then, same exact conclusion as with the ratio test. The series converges absolutely, and therefore converges, if rho is less than 1. The series diverges if rho is greater than 1 or is infinite. And again, the test is inconclusive if rho is equal to 1. You have to try something else. All right, so here are the examples for the root test, and I'm going to point something out to you right now while we're here. Out of all the tests that we talk about, the root test is probably the one I use the least often, and it's because it's only good in a very specific situation, and that is when you have just about everything in your general term is raised to the power n. Because the first thing you're going to do is take the nth root of that. So the nth root will kill the nth power. Okay. All right. So over to the tablet. And here we go. The sum n going from 1 to infinity of 4 to the n over the nth power of 3n. All right, and again, even if the directions hadn't said use the root test, all right, I would probably still use the root test on this one because everything is to the power n. Now, let me just say that sometimes when everything is to the power n, you can actually use geometric series, okay? So think about why is this particular series here not a geometric series, okay? All right, and we'll talk about that a little bit later. Okay, for now, let's look at the limit as n increases without bound of the nth root of the absolute value of A sub n. This series does not have any negative terms, so we don't have to worry about the absolute value. Okay, so it's just the nth root of, and here I'm going to do something here. Instead of 4 to the n over 3n to the n, I'm going to write it as 4 over 3n all to the power n. Okay, because then it's a little easier to see why this and this cancel, I think, right? Okay. So we're left with 4 over 3n. And of course, the limit as n increases without bound of 4 over 3n is 0. And 0 is indeed less than 1. Therefore, this series converges absolutely. It's almost kind of silly to say that a series with no negative terms converges absolutely. But never mind. All right. Yeah, converges absolutely is something we mostly say when the series does have some negative terms, because then, well, the absolute value version of the series and the original series are different series. So it's interesting to think about them both. Okay. All right, next example, the sum n going from 1 to infinity of sine 1 over the square root of n to the power n, the nth power of sine 1 over the square root of n. Okay, so we have limit as n increases without bound of the nth root of the absolute value of a sub n. Okay, now of course sine, S-I-N-E, is negative sometimes. So with this one, we are going to have to worry about the absolute value. So we have the nth root of the absolute value sine to the n 1 over the square root of n. All right, well, what I can do there, again, maybe belaboring the point a little bit, but I don't like to always gloss over these little details. The absolute value of the nth power is equal to the nth power of the absolute value. That is a fact from algebra that I don't think we actually talk about in any class that I can think of that I've taught here. Okay, but that's what's going to allow us to get rid of our nth power and our nth root. So we're left with the limit as n increases without bound of absolute value sine 1 over the square root of n. As n increases without bound, 1 over the square root of n approaches 0. So this limit is equal to the absolute value of sine 0, which is 0. Okay. And that is again less than 1. And so this series also converges absolutely. And therefore converges. All right, and this time converges absolutely is a good thing to say because this series does have negative terms. Actually, I take that back. All right, I didn't think about this. So 1 over the square root of n, the thing that you're putting into the sine function. So first that's 1, and then it's 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4. Think of that as a radian angle, and that angle is always going to be in quadrant 1. All right. So actually, this series doesn't have any negative terms. Okay. Well, now we're prepared for next time when it might. Okay.